Okay, good morning and welcome to the last day of the press conferences at this 53rd annual meeting of the AAS Division for Planetary Sciences. I'm Shantanu Naidu, I'm the DPS press officer and your host today. And with us today are also Rick Fienberg, who's the past AAS press officer. We have Sana Kohler, who's the current AAS press officer, and Carrie Hensley, who's the deputy AAS press officer. There's been a slight modification to the schedule posted on the website. We won't have Mark Bowie joining us. So we'll have two speakers today and two presentations. We'll have Amanda Hendricks, who'll be talking about evaluation of bioburden requirements for the Mars missions. And we'll have Simone Marchi talking about the NASA Lucy mission and its newest target. So we'll have the presenters present in this order, and then we'll have Q&A at the end of the presentations. If you wanted to ask a question, you can use the Q&A box, which is at the bottom of your interface. When you ask your question, please let us know your affiliation and who the question is directed towards. We've asked the panelists not to answer questions using text, so they'll answer your questions during the Q&A session on video. And with that, I'll let Amanda take over.
Okay, thanks, Shantanu. I'm gonna share my slides. Okay, so I'm Amanda Hendricks, and I'm presenting on behalf of the Committee on Planetary Protection, which is a standing committee of the Space Studies Board at the National Academies. And I'm going to talk about a report that is just out now. I've got the link there below the title. And it's a report that we've been working on for the last few months about evaluating bioburden requirements for Mars missions. I thought I'd start with kind of the bottom line, our summary statement from the report, so that you can decide if this is of interest. And what we overall find is that the committee's findings can lead to making portions of Mars more accessible, both to commercial and government endeavors, by relaxing planetary protection requirements, while remaining careful about access to potential habitable zones. And so I'll talk about how we came to this overall conclusion as we go through these. Let's see. Okay, this is a wordy this is a wordy slide with our statement of task. And I won't go through all of these bullets, but I believe these slides are going to be posted so everybody can access this statement later, and it's also in the report, of course. But overall, the idea was that we were assigned by NASA, tasked by NASA to consider criteria and locations on Mars for which bioburden requirements might be relaxed. And what I mean by bioburden requirements is for planetary protection. In other words, in order to minimize harmful contamination to future life detection experiments, we want to reduce the amount of terrestrial microorganisms that might be taken along on missions. But the question is, do all missions really need to go through rigorous sterilization techniques if they're not even searching for life or not even going to places on Mars where we have a pretty good idea that there's no chance of life being there? So this was our overall goal. And there were some underlying tasks that we needed to do too that I'll talk a little bit about and that are outlined here. So some of our important kind of background considerations that we discussed on the committee are for harmful contamination. And again, we want to avoid harmful contamination to preserve future life detection experiments on Mars. We considered the likelihood that microbes will be delivered to Mars, and especially that they could survive and proliferate and be transported across the surface of Mars. And we decided on the committee that one of the biggest factors, risks that we were concerned about is proliferation. So it might be okay if terrestrial microbes survive on Mars, and we don't think they're going to survive very long on the surface. But if they proliferate, then that's the big problem in terms of harmful contamination. And some of the factors that we considered that affect the survivability and growth and proliferation are the temperature at Mars, the amounts of water and the dryness, the desiccation, the atmosphere, and the sources of nutrients and energy, and also the wind in terms of transport across the surface. And as we know, it's very cold on Mars overall. It's very dry, and the atmosphere is not conducive to life as we know it, with low pressure, low amounts of oxygen, and large amounts of CO2. And then, of course, we have wind, though, that even though, you know, it's dry and cold and not conducive to life overall, we do have wind transport that can complicate matters. So these were some of the factors that we looked at. And then in terms of kind of stepping through the report briefly and our big findings, we have an introductory chapter where we discuss previous related reports and talk about our charter and statement of task. In chapter 2, we really present the basis for our report, and we discuss the reasons why Mars is astrobiologically feasible as a target, why we continue to think that Mars could have life, with evidence of liquid water, with Viking measurements that are still under discussion 50 years later, and also after knowing and learning more about survivability in extreme environments of terrestrial microbes here on Earth. So our main, kind of foundational finding that forms the basis for all the rest of our findings is that the future discovery of indigenous life on Mars would be absolutely critical and important for humanity. And so planetary protection is critical in terms of preserving unambiguous distinguishability between terrestrial organisms and any indigenous Martian organisms that are present. So this is just very critical. And we tried to keep this in mind as we went along and came up with our findings. Okay. Then in chapter 3, we had 3 sections. First, we went through what we know about terrestrial life and how it can survive and proliferate, especially under Martian conditions. As I said, at Mars, it's very dry and cold. And in particular, at the surface, the real kind of killer environment is the UV, the solar UV, in particular the UVC, along with the galactic cosmic rays, GCRs, means that anything on the surface, any terrestrial organisms anyway, are not going to survive longer than 1 or 2 sols max. So that, along with the cold and dryness, means that the surface of Mars is not habitable. However, the subsurface, because we talked about special regions on Mars too, and these are regions that have been, for the last couple of decades, been considered to be potential habitable zones, potentially places where liquid water could be present, for instance. And we came to the conclusion that these special regions, such as caves on Mars, lava tubes, are largely in the subsurface. We don't find any special regions on the surface. So what we're mainly concerned about in terms of proliferation is all in the subsurface. And mainly we ended up focusing on caves here. We know that on Mars, there's, at least about 1,200 cave openings that have been found from high-rise imagery. Importantly, though, high-rise at its highest resolution is only imaged maybe 3% of the surface of Mars. So there could be more cave openings, access to potentially habitable zones in the subsurface that we don't know about. And we also don't know much about those caves at all. So the main risk that we're concerned about in terms of proliferation is not on the surface, but it's in the subsurface. Okay. So now I want to go into the criteria for the landing sites. This is the third part of our chapter 3. So the criteria that we came up with to find landing sites that might be able to have reduced bioburden requirements, so less stringent cleanliness requirements, for instance, pre-launch. And these criteria were largely driven by where the water is on Mars, and also how interconnected we think the subsurface is, especially, potential brine networks that could be present, and also where we have access to the subsurface and where there might be other astrobiologically interesting sites. So we need to know, again, where the water is, where the potentially habitable zones are, and where other sites that we might want to preserve are. And we came up with this map here based on the most recently published data. And this is a map showing you Mars from 60 south to 60 north latitude. And this tells us where we think the water is in the top meter of the surface from thermal IR and neutron spectroscopy. And what I'd like you to focus on here is the gray areas are where we think there's very little water in that top meter. The more colorful areas have more water. In the gray areas, there could be water, certainly in the top meter, but we expect that it's probably going to be patchy. And so again, if terrestrial organisms were able to access a patch of ice in the top meter of the surface in one of these gray areas, that might not represent harmful contamination because they're probably not going to proliferate then if it's just a one little area of ice. But if there are areas where we think there could, again, be interconnected networks in the subsurface where life could then proliferate, that's what we want to avoid. So all of these gray areas, there's very little ice in the top meter. The black dots are where are the locations of those cave entrances that I talked about. So again, in terms of finding areas where missions with lower bioburden requirements might be able to land, we would select these gray areas, but staying some safe, conservative buffer distance away from these black dots where the cave access points are, and also away from other astrobiologically interesting sites where, for instance, clay deposits where maybe there's evidence of past Martian life. So to kind of summarize, we had a summary conclusion in a box in our report, and mainly based on this map that I just showed you, and because of our knowledge about the sterilizing conditions of the Martian surface, largely due to the UV, we concluded that bioburden requirements could be relaxed if missions do not, include subsurface activities at all. Maybe landing anywhere on the surface is okay because the surface environment is so biocidal. If missions want to have surface activities as deep as a meter, again, they'd want to land in one of those gray areas. And for both of these cases, the landing site would need to be a conservative distance from any of those subsurface access points. And we went through an exercise in the report to provide an example of such a conservative distance, where we take an average wind speed, we take a time period over which we think any lofted terrestrial organisms might survive. So again, max 1 or 2 sols, but we could say, okay, maybe 15 hours. We can say within 15 hours, a terrestrial microorganism is not going to survive, but how far can it be transported in that time? Could it potentially access a cave? Okay. And then finding 7 I haven't presented all of the findings in detail, but I wanted to present finding 7, which in which we concluded that for any of these missions with relaxed bioburden requirements, we didn't go into details, and it was kind of out of our charge to go into what do we exactly mean by reduced bioburden requirements. How many what's the spore count on that? We didn't go there, but what we did say is that there do need to be some pre-launch cleanliness provisions taken by such missions. Maybe they don't need to be as restrictive as current Mars landers, which is called Category 4. But they do need to have some pre-launch cleanliness. It wouldn't be appropriate to build a spacecraft in your garage and then launch it. You've got to, even if you're going to one of those gray areas, you've got to do some sterilization, some cleanliness. Okay, and then we also looked at the overall situation with NASA's planetary protection requirements and found that they rely primarily on pre-launch spore count measurements, and they're pretty limited and pretty lacking in flexibility. And so we looked at some alternative techniques that NASA may wish to implement for some of these missions with relaxed bioburden requirements, for instance, or maybe even other missions too. And so in particular, we kind of focused on a risk management approach as a nice alternative that NASA may wish to consider using. And this is something that's used all the time in aerospace industry, for instance. And then we also thought about in situ bioburden reduction, perhaps using the native UV flux coming in as a sterilization technique. That could be another way of, an alternative way of doing planetary protection implementation for some missions. The risk management approach would, for planetary protection, as for other areas in which risk management is used, it might be a 4-step process where missions might assess the various ways in which they might produce harmful contamination, what the situations are that can produce that contamination, and then look at the likelihood and consequences of those possibilities. And then when we think about risk, we think about kind of the product of likelihood and consequence. And so we can then rank those risks from low to high, and then identify mitigation measures so that we can remove all of the high risk situations. An example risk matrix that we came up with that could be used for Mars missions, as well as perhaps for other targets, shows consequence in the horizontal direction and likelihood in the vertical direction, from low to high. So you can imagine a situation of low likelihood and low contamination, low consequence, I should say, for a mission that's super sterilized, and it's a robotic lander, and it lands in an area where there's no risk of, they're not searching for life. There's no evidence that there ought to be life anywhere near that area. That could be like a 1-1, a very low likelihood, low consequence situation. But in the other part of the risk matrix, you might have a very high likelihood, high consequence situation. For instance, if you're sending humans to Mars and they are walking around a cave entrance and, just sort of with every step, emitting biofilms and so forth. So that's a situation where you'd want to try to deal with and mitigate these risks before launch using some technique as appropriate for that mission. So that's a summary of our report. I'd be happy to take questions. And I wanted to leave you with a list of our members. I'm the co-chair of the committee along with Joe Alexander, and Daniel Nagasawa is the study director. And we've got 15, experts in various fields on our roster. So I'll let you study those. And I then put our bottom line again over here about making our findings, hopefully making portions of Mars more accessible, both to commercial and government endeavors, while keeping cautious about access to potential habitable zones. And then here's a link to our report. Thank you very much.
Okay, we'll have Simone give his presentation now.
Can you confirm that you see full screen my presentation?
Yep.
All right. Good morning, everybody. Thanks for being here today. My name is Simone Marchi from the Southwest Research Institute in Boulder, Colorado. And today I will be talking about, giving an update about the NASA Lucy mission. And I'm also the deputy project scientist for the Lucy mission. I would like to get started with a little bit of science motivation and driver for this mission. Lucy is going to be the first mission to explore the Trojan asteroids. As the plot to the right shows, the Trojan asteroids are found in two large clouds of objects leading and trailing Jupiter along its orbit around the Sun, and those asteroids have never been visited before by spacecraft at close range. An interesting and intriguing aspect about the Trojan asteroids is that they come in different flavors. It's a very heterogeneous population. They come with different colors, possibly indicating different compositions. There's ranges of albedos, sizes, of course, and with implications for different evolutions. The Trojan asteroids really represent an opportunity for us to study the earliest evolution of the solar system, and in particular, the migration of the giant planets. So we think that these objects have been captured in their current stable position thanks to this early shifting of the planets. And so by studying them, we can learn more about the formation of those planetesimals early on and how they were captured. Other important aspect excuse me. Another important aspect about the Lucy mission is the large number of Trojan asteroids, 7, that will be visited. This would allow us to do comparative investigation among those objects. A little bit more now about the payload and investigation to be carried on by the Lucy mission. What you see here is a rendering of the spacecraft. The payload is on top. It's found on a platform here. So all the main instruments are to be found on the platform. And we have 4 instruments there. We have LRI, which is a visible imager, high resolution imager. We have LRALF, which is a combined instrument that contains both a color visible imager plus an infrared spectrometer. LTES is a thermal emission spectrometer. T2CAM are 2 cameras that will be used for tracking of the spacecraft, but also will provide additional scientific data. And finally, we have the high gain antenna that will be used to track the motion of the spacecraft as it goes by the asteroids to infer the mass of those objects. All of these payloads will inform a comprehensive set of scientific investigation ranging from surface geology, surface colors and composition, trying to assess the internal properties of the objects by looking at the volume and the mass, and also search for satellites and rings. Really, the key aspect of the Lucy mission is its amazing trajectory. What you see here is the trajectory of the spacecraft as it unfolds and in a frame rotating with Jupiter. So this is perhaps a little bit unfamiliar representation. The trajectory of the spacecraft is in green of this chart. After launch, there's going to be a couple of loops in the inner solar system. And then the spacecraft adds towards the first clouds of Trojan asteroids L4. Here we'll have a sequence of multiple flybys with different objects. After that, the spacecraft will come back to close to Earth again and then shoot out in to the L5 cloud, in which we'll have the final flyby with Patroclus and Menenichus. The timeline for those events are indicated at the bottom of the chart. It is a 12-year mission altogether. I also want to point out that as we go, we leave Earth and we go through the main belt before reaching the Trojans, we have a chance to fly by a small main belt asteroids to give us an opportunity to test our instruments. Let me now present you with, if you will, a family picture of our targets. These are the main targets, Trojan asteroids that we will study. Obviously, this is an artistic conception. We don't really know what we'll find on their surfaces. However, the sizes of this object have been scaled thanks to what we know about their true sizes, thanks to telescopic observation. The other interesting information that you'll see on this chart is the color of the surfaces of this object, which reflects what we know about of their spectroscopy spectra properties. So, for instance, Eurybates, which is the first flyby, the first Trojan flyby we will do, is so-called C-type asteroids. That simply means it's a relatively gray surface. And then we have other spectral type known as P and D. That simply means P is a little bit a red object, while D it's a very red object. So this is to show that we'll sample the ranges of sizes, but also ranges of colors, which is one of the key aspects of the Trojan asteroid. And with that, I think I want to give you some exciting news and talking a little bit more about one of our targets, that is the Eurybates, the first flyby that we will do of the Trojan asteroids. Why Eurybates? It's important. What do we know about it? Well, first of all, this is really an intriguing object because it is the parent body of a so-called asteroid family, meaning a class, a number of objects that have been formed by a catastrophic disruption of a larger parent body. So Eurybates really gives us the opportunity for the first time to explore the survivor of a catastrophic collision that presumably happened billions of years ago. So that's very exciting from a scientific point of view. We also know, as already anticipated in the previous slides, that Eurybates belong to a peculiar class, an uncommon spectral class, being a C-type, a gray object. And so that would be particularly important as well. What you see here is the best estimate of the shape of the object that we have so far. This is based from ground-based observation of the object. The average size is about 64 kilometers in diameter. So what is new about this target? Well, the Lucy science team used the HSE, the Hubble Space Telescope, to perform a deep survey around the object to search for satellites, and lo and behold, we found one. The object has been named Keita, and it's about 1 kilometer in size, and you can just see it with your eyes on this cover image down here. We also know the orbit of this object, which has a period of about 84 days, and so that's what we know so far. Certainly we will do more observation in the future to better characterize the orbit. I also want to stress out that this is an additional target for us, but it's a target of opportunity, meaning it does not belong to the primary list of targets that the Lucy will have to observe. So in other words, we will do our best to observe it. Another interesting aspect related to the discovery of a satellite is whether or not that poses a risk, a collision risk for the spacecraft. What you see here on this plot to the right is the projected trajectory of Lucy as it approaches Eurybates. The close approach distance is about 1,000 kilometers. And the red distribution of dots there shows you where we think Keita would be. Now, this plot here shows that potentially we are close in this projected plane. We are just looking at 2 dimension here on Keita on this side as we approach. However, if you look at the other dimension, the Z dimension, we'll see that we are far enough from the expected position of Keita. So in other words, we don't think that this poses any risk whatsoever for the spacecraft. Now I want to show you a couple of more recent pictures. This is a picture was taken just a few days ago, and we are dealing with finally the encapsulation of the spacecraft within the Atlas V401 fairing. This is really the last moment we could see the spacecraft with our eyes. After that, the fairing was closed and the spacecraft is hidden for our sight. All is on track for an October 16 launch. This is next week, so stay tuned for more exciting discussion next week. And just amazing to think that, you know, after many years of working and building a spacecraft, this is really the last moment we have the chance to see it with our eyes. And the next time that Lucy will leave the fairing of the rocket, it will be spaceborne and headed on its way for a 12-year 4 billion miles journey to explore the Trojan. And with that, I will stop here. We certainly wish Lucy safe travels, and I will be happy to take any questions.
Okay, and we'll have Q&A now.
All right, I'm going to take the questions and read them aloud for you. So we do have a few questions queued up. The first two are for Amanda. The first one comes from Alex Witze, who's writing for Nature. She asks, to what extent, if at all, do you expect your team's findings to be used in non-NASA missions, such as those run by other space agencies or even by commercial companies?
Okay, right, good question. We talked about this, and it was actually part of our statement of task to consider the idea that it's not just NASA going to Mars anymore. And we have representation on the committee by experts with commercial experience, either currently working for commercial companies or who have in the past. So it's great to get their insights. And we also have a representative from ESA in science and management. So we had a lot of good inputs. And the hope is that, of course, all missions to Mars will follow planetary protection guidelines to keep, to preserve future search for life and astrobiologically related science in the future safe and uncontaminated. Right now, I mean, our report was commissioned by NASA, but we were asked to consider commercial interests. That being said, NASA is not a regulatory agency and does not oversee the planetary protection implementation for non-NASA missions. There's plenty of missions led by commercial companies with NASA contributions. And so they would be overseen by NASA planetary protection guidelines. But ultimately, there's a gap in the regulations in terms of oversight of planetary protection for non-NASA missions. And this is a problem that we point out in the report. COSPAR, which is a Committee on Space Research, which has representation by NASA and lots of different countries, and the national academies, is ultimately the body that we look to for oversight of all of the planetary protection guidelines in terms of international participation. But the gap in regulations for non-NASA missions for oversight of planetary protection guidelines is a problem that we hope that that will be dealt with in the near future, so that we won't end up with problems for Mars missions in the future.
Okay, thank you. The next question, also for you, this comes from freelancer Rick Lovett. This is concerning planetary protection. Is there a way to apply HAACP techniques as developed by NASA for preventing foodborne illness in space and now widely used in the food industry? And I had to look up what that acronym stood for, and it appears to be Hazard Analysis Critical Control Point, something that the FDA uses now to keep our food safe in the grocery stores.
Great, and that's a great question. We did consider sterilization techniques that are used by other industries, aerospace industry, food industry, medical and healthcare industry. And we look to these as standards that could be applied as alternatives to the current implementation techniques that NASA uses. They're obviously very concerned about sterilization as well for their applications in food and medical industries. And so we did point to those in our report, and we heard from an expert for information on these types of things. And in terms of sort of allowing some flexibility for NASA missions in their planetary protection implementation techniques, we feel like these could be good options. And so all we can do is really encourage NASA to look into these in our report, but we think it could be a good idea.
Okay, thank you. The next question is for Simone Marchi. This comes from Alex Witza again at Nature. What observations will Lucy be taking on approach to all its targets in order to hunt for dust or satellites that could pose a risk to the spacecraft? How much maneuverability does Lucy have to physically avoid any such risks if they are found?
Yes, I think there is little possibility for the mission to change the trajectory, in months leading to the flyby. So any observation that will be done far away from the target would potentially, inform us about small satellites, perhaps, but there's going to be little chance to maneuver the spacecraft. I also want to say that we had conduct an in-depth investigation whether or not there is a reasonable risk from dust that could be lifted from the surface, and the conclusion is that there is basically no risk given the distances from which we will fly by from the surface. So we expect that the dust would not pose any risk for us. When it comes to larger objects, satellites kind of objects, those are extremely rare, and they're not going to be in great numbers. So again, it turns out that the risk, we think the overall risk it's minimal at all. So the kind of observation that we plan to carry on for satellites and potentially any form of dust, it's more for the science that we will get out of it, not necessarily because we are concerned about any risk. But back to to your question, in order to be able to change the orbit in a significant fashion, that will have to be known many months in advance, possibly even a year in advance. So that's sort of the timeline for which we can react.
Okay, there's a related question here from astronomer Ned Wright at UCLA. He asks, does Lucy have an ion drive or a more traditional chemical engine?
Traditional chemical engine.
Okay. All right, now one more question for you, Simone. This is back from Rick Lovett, again, freelancing. He says, I gather you achieve that visit of both groups of Trojans by a carefully constructed, highly elliptical orbit that uses Earth to divert its aphelium from one group of Trojans to the other. Then he puts a question mark at the end of that. So how are you scooting from one set of Trojans at L4 to the other at L5?
Yeah, that's a very good question, and it goes at the core of the trajectory of the spacecraft, which is really the key point of this mission. Is a well-thought trajectory that will allow us to do all those great things that we discussed. It is not quite as you described for the following reason. Once we launch, there's going to be a couple of loops in the inner solar system. Basically, in those two loops, we'll have a flyby with the Earth. In both cases, we will use the gravity assist to put Lucy on an elliptical orbit. So that is done with the second Earth flyby. As the result of the second Earth flyby, you can imagine an elliptic orbit in which the aphelion is to L4 and the perihelion is close to Earth. So that is achieved with the last Earth flyby. Once you are on that elliptic orbit, there isn't anything else we need to do. It just works out beautifully, because the first loop we go out would allow us to go to the L4. And the timings are such that as you go along that elliptic orbit, you come back to 1IU and you go out again. By the time you go out, you are already headed to the L5. That's the way the period of the revolution of the Trojan works with respect to the period of the spacecraft on that elliptic orbit. So we do not need another kick to get to L5, but we do need a kick to get to L4. And once we are on that path, it's all done.
That's fascinating. Thank you. Now we're going to come back to a question for Amanda Hendricks from Irene Klotz at Aviation Week and Space Technology. How long does the team estimate restricted zones will be needed on Mars, especially since sending humans there is the whole point of SpaceX?
Let's see. So that's an interesting question. First of all, I'd like to clarify that we didn't really think of these areas as restricted zones. As a matter of fact, we kind of are trying to help open up Mars a little bit to some types of missions that aren't going after life detection, in order to simplifying planetary protection implementation. So hopefully it's not so much of a restricted zone as kind of a, a little bit more open zone while being cautious. And we'll have to see how it goes in terms of time scale. I think we'll have to see how it goes with, if NASA decides to implement this advice, we'll have to see how it goes in terms of, how many missions end up using reduced bioburden requirements, and how they implement perhaps simplified implementation techniques take place. So I'll hold off on giving you an exact timescale on that. But we did consider briefly any implications for humans going to Mars. And what we came up with is that it's such a different ballgame for humans going to Mars than for robotic missions going to Mars, that we might be able to learn something about planetary protection techniques and implementing more flexibility into them with these steps. But how applicable they will be to human missions is still unclear, because they are so different. Another point of importance is that planetary protection policy for human missions is not well developed at this point. It has been looked at in the past, but as we move forward with potential human missions to Mars, it's really going to need a close and careful look again more currently.
All right, thank you very much. And now we're going to come back to Simone with a question from Megan Bartels at space.com. Have there been any observations of Keta gathered since the initial discovery work? What are the opportunities for learning more about it before Lucy's arrival?
Yes. there was a hiatus in the possibility for us to observe Keita from Earthbound facilities, but now we have planned more observation with the Hubble Space Telescope. So hopefully we will get a better knowledge of the orbit and additional properties, and maybe better constraints on the size of the target. So there will be more observations, but there is a limit of what we can do with Earthbound observations, and so it's not like we can continually observe this object until we get there. But definitely there will be more observation in the upcoming months.
I have a follow-up for that myself. If you, I mean, it's going to take a while to get to the Trojans, and with any luck, the James Webb Space Telescope will be up before you get there. Are there any plans to try to do any pre-encounter observations with Webb?
Yes, there are indeed. We are scheduled to carry on an observation program for our target. So yes, that will be done.
Yeah,
not for
would be
Keita,
exciting.
obviously, because that's going to be too faint. But for the primary target, yes, we have that planned.
Great.
I had a question for Simone.
Yes.
Do you plan on leaving the Lucy spacecraft in that orbit after visiting the last object? And if you do, would you be able to resample objects in L4 and L5, and how long will it take, if that's a yes?
Yes, that's an interesting question. In principle, the spacecraft will remain on that elliptic orbit for a long time. So that would allow us to do several things. Cross the main belt back and forth many times. Every time you cross the main belt, there could be an opportunity to observe some main belt asteroids. As a matter of fact, we already know that we may come close to some interesting main belt asteroid after the last Trojan flyby. But yes, in principle, we may be able to access the Trojan clouds again and again in the future. So the idea would be then to ask NASA for more and more fundings for many years down the road to keep using the spacecraft as an observatory, both for main belt asteroids and for Trojan asteroids. So yeah, hopefully we'll be able to do some of that.
But if you're going to see L4 on the first pass and L5 on the next pass, by the time you get to the next few passes, Jupiter and its Trojans will have moved further around the sun, right? So it would take a few more orbits before you came back to the Trojans.
Right. That's correct. Yeah,
So
that is true. That is true. But in principle, that orbit is relatively stable for, say, millions of years time scale. And so that would allow, so many times to repeat that, of course. There is a question about protection that we had to consider, whether or not the spacecraft would remain on a stable orbit by colliding with any other relevant target for, say, astrobiology, just to connect to Amanda's topics as well. So we don't want to contaminate any possible interesting target. And so we know that orbit is stable, relatively stable, millions of year time scales. But I would say that better chances for us would be to perhaps try to observe main belt asteroids, because that would be relatively close after the last flyby of the Trojans, and so that would really be the only, I guess, opportunity. We cannot really keep operating the spacecraft forever.
A couple more questions have come in the last few seconds. These are both for you, Simone, from Alex Witza at Nature. What is the limiting factor for survival of the spacecraft? Is it propulsion or something else?
Oh, it's probably both. Propulsion is used to control the spacecraft, but also for steering the spacecraft. Say you want to change a little bit the direction of the trajectory because you want to go fly by an interesting object. So that, unless you're extremely lucky that it's already on your way, you have to steer the spacecraft to do that. So doing those maneuvers will take energy, as well as to stabilize the spacecraft. So it's a combination of those things. That it's more likely to be the limiting factor for being able to operate the spacecraft for a longer time. In terms of celestial dynamic stability of this orbit, as we said, it's very long-lived stability. We're talking about millions of years. So that that wouldn't be a concern. At some point, though, we may run out of fuel to do all those maneuvers, unless we are extremely lucky and it just happened that we can fly by without consuming much fuel of some other interesting main belt asteroid.
Is the instrument platform steerable, or do you have to steer the entire spacecraft in order to point your instruments?
It is steerable in 2 axis dimensions. Of course, one of the two has a wider range of motion than the other one, but it is steerable in both dimensions. And that gives us some more freedom during the flyby, because the pointing at the surface is not just done by rotating entirely the spacecraft as a solid object. We have those additional 2 degrees of freedoms that we can use to achieve better pointing, better performances.
Okay, and then Rick Lovett, freelance, had a follow-up to Alex's question, but I think you may have already answered it. He's saying, how long can the spacecraft possibly survive? Will it run out of power or consumables? And you mentioned that the main consumable is fuel for propulsion and maneuvering. It's solar powered, right? So you have those
correct.
2 giant solar power panels. So as long as it can continue to charge its batteries, it should be fine, right?
In terms of power, yes. Those are extremely large solar panels. You may recall from one of the charts I had with the rendering of the spacecraft. These are 7.2 meters diameter each solar panel. And those are needed in order to get power of 5 AU. That's very far from the sun. So we need those high efficiency, very large solar panels. But once we are locked on that orbit, we already know that we can survive at the aphelion, which is about 5 AU. And so the power would not be a limiting factor, mostly fuel.
Okay. And Irene Klotz from Aviation Week is back with a quick question for Amanda. Does the Planetary Protection Report address decontamination levels for Mars orbiters?
We did not. We were tasked with looking at Mars landers only. That currently are at what's known as category 4, A, B, or C, and whether that can be reduced from category 4. But orbiters are category 3, and we didn't tackle those at all and weren't asked to. Maybe for a future one.
All right. Well, it looks like we have exhausted the questions, and that's good because we're close to exhausting the time. I'll turn it back over to, oh, Amanda, you have a question for Simone?
Quick plug for a webinar that's being hosted by National Academies about our report today at 2 p.m. Eastern. Might be of interest to some people.
And back to you, Shantanu.
So with that, we'll end this press conference. Thank you to the speakers for these exciting talks, and also to the audience for their participation and keeping the discussion lively. And also thanks to all the PIOs who helped with press releases and press briefings. And finally, we would like to thank USRA for sponsoring the press conferences. It's been lovely having everyone, and hope to see most, if not all of you, at the next DPS, which could be in person or on or virtual. Okay, thank you, everyone.
Thanks, everybody.
Thank you. Bye-bye.